from last night, this was the problem that Luke left with you. So a popular computer card game keeps track of the number of games played and the number of games won on that computer. Okay, again, I just call this setting the stage. It feels like you either win the card game or you don't win it. You win or lose. The cards are shuffled before each game, so the outcome of the game is independent from one game to the next and is based upon the skill of the player. Okay, that makes sense. I like that independent word. Let X represent the number of games that have been won out of 100. So we're playing just 100 games, or a total of 100. That's a finite number. So I'm leaning towards binomial here, but let's keep reading. Under which of the following situations would X be a binomial random variable? Okay, so we're in a binomial setting here. Again, here's the same problem. So before I actually started to work on the problem, I just made some real quick notes down here to myself. When I think of a binomial setting or binomial probability, I think of four things that I need. And I know Luke talked about this yesterday. We have two outcomes: a success and a failure, win, loss, in, out type of deal. We have independent trials. Well, we did see that word up here somewhere, so that was good. So it feels like we've met that condition. The number of trials is finite, meaning fixed, or we can count them, it stops. Determined in advance. Well, I think we had that, right? Didn't it say we were going to play 100 games? So that feels good. It feels like I've met those two. I guess I have met the first one as well, right? We either win or lose the game. It didn't actually say lose, but it feels like we win or lose. And so I kind of focused in on this fourth one here, the same probability of success for each trial. So that's sort of what I was looking at before I did the problem. So A, all games were played by the same player whose skill improved over the course of the 100 games. Well, if your skill is improving, that feels like your probability of success is changing. So I don't think it was that one. A group of 5 players of different skill levels. I think I honestly stopped right there and said, well, different skill levels, that means different probability. It's not going to be that. A group of players of different skill levels. That again, that was sort of my little clue there. So I think I crossed that one out. 2 players of equal skill each played one game a day for 50 days, and their skill level did not change from day to day. So I sort of like that one, but to be honest with you, I said, well, 2 and 50, is that going to be the same as one person playing 100? So I wanted to keep reading. D felt pretty good to me, but I did want to just sort of keep reading and see what E told me. So 2 players of different skill levels competed, and so I actually did cross that one out. And so the answer is D here. And I actually really like this. Luke and I sometimes talk about the problems we're going to pick, and sometimes we don't, and we just surprise each other with what the homework is for the next day, and he and I have to sit down and do it. I really like that. I can't remember a problem in my textbook where, we said 100 games where we had 2 people. So that felt really cool to me, and it was a little different, and so I really like that, and hopefully you guys really like it as well too. I had to think about it, and it was a good little problem. So anyway, that was from Luke's session yesterday. So again, there's just some websites. I think this has been a typical slide of mine. Anything, all updates on your exam are here. You can find the schedule for what we're doing. There's more information coming, so stay tuned. And I do think at some point we're going to have like a practice as to how you can upload, some more details as to how you can upload your answers. So stay tuned for that. College Board's working probably 24/7 to try and get this ready in a short period of time. More good stuff coming. Stay tuned. How's that? So today we're going to talk about random variables. And so the value of a random variable, the values of a random variable are the numerical outcomes of random behavior. Okay, makes sense. A discrete random variables. So discrete just means that there's a finite number of outcomes. I can count them, et cetera, as opposed to infinite. So we do a lot of discrete random variables in this class. So a discrete random variable is a variable that can only take a countable number of values. We know how many there are. Each value has a probability associated with that, so I can calculate the probability of that. And we talked about this, I think, on Monday when we talked about the sample space. The sum of the probabilities over all of the possible values must be 1. Super important, and I'm going to use that when I actually start to do some problems later this afternoon. I want to make sure that all of my outcomes add up to 1, and that sometimes helps me solve the problem. So, you know, I like to think of a random variable in its super simplest terms is a random event where I perhaps know what the outcomes could be, but I just don't know what's coming next, and that's the random behavior. So if I flip a coin, I realize I'm going to get heads or tails. I just don't know what the next outcome is going to be. If I roll a 6-sided number cube, a dice or a die, I know I could get a 1, 2, 3, 4, 5, or 6. I just don't know what's coming next. I can quantify each one of those outcomes and put an associated probability. And so I would define those as random variables. We're going to talk about adding means and standard deviations and whatnot. And so for 2 independent variables, x and y, we can add the variances. We cannot add the standard deviations. That's a little tricky. My students will sometimes struggle with that. And I think I have 2 multiple choice that try and get right to that topic. So I can add and subtract means. That's logical. I can add variances, assuming my events are independent. I cannot add my standard deviations. And so I have a couple problems that will hopefully get to that. And that's a little bit at times difficult for my students. So this is an oldie but goodie. This is from the 1997 exam, actually the Acorn book. And I actually sometimes give this to my students before we've talked about random variables. I just sometimes like to give them a problem and see what they can do with it. How's that? And so this one is an oldie but goodie. I really like this. And that being said, my students don't like this. They don't like this nomenclature here at the top. X and probability that big X equals little x, Y, probability of big Y equals Y. They don't like the nomenclature at all. And so sometimes this is, you know, what I might call like, you know, a good classroom problem where we do it together. But when I give this to them and give them 5 minutes to do this, yeah, they typically do not like this at all. So give me just a second here. Okay, so there's the same problem here. Sorry, there was like a little green outline in my screen. I don't know if you saw that. So here's the same problem. So we have some tables up here. X, probability of X equals little x, probability of Y equals little y. I'll demystify that. The tables above show part of the probability distribution for random variables X and Y. So the big X and the big Y, those are my 2 different random variables. That's all they are. If X and Y are independent, super important, and I'm probably going to underline that. And the joint probability that big X equals 3 and big Y equals 4 equals 1/16, and the probability that big random variable Y is equal to 1 is equal to, and honestly, my kids really, my students struggle with this. So big X, that's one of my random variables. Big Y is my other random variable. And over here on the side, I've just tried to demystify. The probability that big random variable X is equal to 1 is 1/6. So that's what that line's trying to tell me. The probability that big random variable X is equal to 2 is 4/6. I think I just made 2/3 4/6. The probability that big random variable X is equal to 3 is I don't know. Well, you can see that I did a little sigma equals 1, meaning if I add up my 3 outcomes, my only 3 outcomes, I have to get 1, right? We talked about that a little earlier. So So that was 1/6. So this first question mark over here is 1/6. I think if these numbers were all the same, which they're not, that's a good thing. I think it's real easy for students to say 1/4, 1/4, 1/4, and 1/4. That doesn't have to be true. The probability of each one of these outcomes in a random variable does not have to be the same. And that's why I like X so much over here, is those three probabilities are not all the same. So I set up a little equation here and I said the probability that big random variable X is 3 times the probability that big random variable Y is 4 is equal to 1/16. I was given that, so I was told that. Well, the probability that big random variable X is 3, that's 1/6. So I felt comfortable with that. Feels like I'm kind of solving for this. So 1/6 times this number here is 1/16. I think I just multiplied both sides by 6, multiplied both sides by 6. And I get 6/16 is the probability that big random variable Y was a 4. So I'll just go and fill that up in here. So 6/16. And again, I do know that if I add these four numbers here, I would get 1. I know that the sum of my discrete outcomes is always going to be 1. So I think I just made that 4/16, 4/16. So this number plus 4/16 plus 4/16 plus 6/16 has to be 16/16 or 1. And so when I was said and done, I did the math. I said, well, the probability that big random variable Y was equal to 1 is 2/16 or 1/8. So my answer was A. I just love this problem. It really helps my kids sort of feel comfortable with this nomenclature, my students, that what this nomenclature is. They don't means every 3 years. In a large school, it would be not atypical to get over 1 million copies in 3 years at a school. So they get a tremendous amount of use. Lots and lots of teachers making lots and lots of copies. They get used quite often. The repair contract for machine A costs $50 per month and covers an unlimited number of repairs. So if it breaks down once in a month, I pay $50. If it doesn't break down at all, I pay $50. If it breaks down every day, I pay $50. So that's one plan. That's one way that our school could purchase a copy machine. The repair contract for machine B costs $200 per repair. So I guess I'm trying to figure out like which plan is going to be more cost effective for my school over the next 3 years. There's 2 different initial costs for the machines, and I guess there's 2 different potential repair costs for the machines. Based on past performance, the distribution of number of repairs over a 1-year period for machine B is shown below. So it looks like maybe machine B, we can either have 0, 1, 2, or 3 repairs. I wish our machines were that good, were that dependable. It feels like ours break a whole lot more than that. Here's the associated probabilities. And again, I would probably just add those up, 0.75, 0.901. So we talked about that. The sum of the probabilities of a discrete random variable always needs to be 1. I just want to kind of confirm that. You were asked to give a recommendation based upon overall cost as to which machine A or B, along with its repair contract, should be purchased. So you have to make a recommendation to your principal in your school, should you purchase machine A or should you purchase machine B? And this is super real world. Do we get a variable mortgage or a fixed mortgage when you buy a car? So this is a great problem. Anyone who's heading off into the business world or studying business in college, you'll do thousands of these problems. What would your recommendation be? Give a statistical justification or support your recommendations. Even if that last sentence wasn't there, please always show your math. I'm sure Lucas is saying the exact same thing. So for machine A, cost $10,000 to buy. It was $50 a month. It was 12 months in a year, and it was over a 3-year window. So I multiplied 50 times 12 times 3, and I got 1,800. So the total cost for machine A with repairs for 3 years is $11,800. keep in mind that that's unlimited repairs with this option. Okay, machine B, its initial cost was $10,500, so a little bit more. But the repairs, we don't really know perhaps how many repairs there would be. So I had to calculate the expected value. So down here I said, you know, the outcome times its probability plus the outcome times its probability plus the outcome times its probability. And so we expect, so we would call this the expected value, right? Expected number of repairs. We would expect 0.85 repairs a year. Now I mentioned, I think on Monday, we do not want to round that number, okay? And students say, but Mr. Murphy, you can't have 0.85 repairs, and that's a true statement, but we do not round expected values unless specifically told otherwise. So I think there's my initial cost for machine B. There's my expected number of repairs per year, 0.85. We were told it was $200 a repair, and we want to do this for 3 years. So when I did that math, I got 10,500 plus 510, 11,010. And so if I'm looking at these two numbers here, clearly machine B is, well, let me rephrase that. We think that machine B will be less expensive, but there's no guarantees. But most of my students will say, you know, let's pick machine B. And so over here, I just added a sentence and said, I would choose machine B as I would expect to pay around $11,010 over the 3-year window, as compared to $11,800 for machine A for initial purchase and repairs. So that's what most students will pick. That's what most of my students will answer. You could make a strong argument that this is a better plan because it has unlimited repairs. So in other words, machine B, if you have not 0.85, that was what we expected, but maybe you could have 10 repairs a year. Well, that would be 10 times 200 times 3. That would be a whole lot more expensive. So this is a problem that you could actually answer 2 different ways, depending upon your perspective. I argued on what I expect to spend. This would be less than what I would spend here. But I think you could have a strong argument saying, you know, even though this plan is around $800 more expensive, it's safer, perhaps. And the fact that it covers unlimited repairs. So really neat problem, because I think you can argue it or present your answer sort of 2 ways. And that's very, very real world. You know, fixed mortgage versus variable rate mortgage. You know, do you lease a new car? Do you buy a new car? Do you rent? I mean, there's all these options, and some of it depends upon your financial comfort level. So kind of a neat problem where I had to use expected values and probabilities and whatnot. And so I really like that one. Let's see if we can do at least 1 or 2 more. So this was from the 2015 exam, sorry. So a little bit more recent. The shopping mall has 3 automated teller machines, ATMs, just setting the stage. Because the machines receive heavy use, they sometimes stop working and need to be repaired. Okay, that makes sense. It is frustrating, right? When you go to an ATM, you put your card in and it tells you that the machine's not working. Let the random variable X, okay, so again, typically uppercase, represents the number of ATMs that are working when the mall opens on a randomly selected day. So I like the randomly selected. Big X is my random variable. And I have three machines, 3 ATMs at this specific mall. So this little table down here, number of ATMs working when the mall opens, none, 0. That is an option, and sometimes students forget that. You know, sometimes students say 1, 2, or 3, Mr. Murphy. Well, I guess none of them could be working, and that would be terrible, right? I'd have to walk around and to go to 3 or 4 different machines, and none of them would be working, right? Probability of that is 0.15. 1 machine working, 0.21, 2 machines, 0.40, 3 machines, 0.24. When I first did that, I thought that actually number might be higher, but it does look like, just looking at these numbers, that many times not all three machines are working. How's that? I think I'll add those up real quick, and looks like I get one. That's sort of good. That happens with random variables, so I felt comfortable about that. And so part A, this maybe was I don't know if I did, I don't think I did this one on Monday, but maybe part A and part B are more what I did Monday, but it's a nice problem, so I want to do all four parts. What is the probability that at least one ATM is working when the mall opens? Well, one working is at least one, two working is at least one, three working is at least one. So I think in part A, I said the probability that my big random variable X is greater than or equal to one, at least one machine is working. I just added those three probabilities and got 0.85. Again, notice that I have those numbers on my paper. I want to make sure that I'm showing the reader my mathematics. And then sometimes I step back and say, is that enough, or should I probably include a sentence? And I wanted to include a sentence. So the probability that at least one ATM is working when the mall opens is 0.85. So that felt relatively easy. I was confident that I could do that relatively quickly, but sometimes we just see, 0.85, and students have added those three numbers on their calculator. And I'm going to say, to be safe, show us your work, show us your work, show us your work. How's that? Almost never will showing your work hurt you, and almost always showing your work will help you. So just be careful about that. I think I would show that work, and that's what I tell my students. What is the expected value of the number of ATMs that are working when the mall opens? Okay, so outcome times probability plus outcome times probability plus outcome times probability plus outcome times probability. So you see I did that math here. And I think I had the expected number of the number. Well, that didn't make sense. So I crossed that out and said, well, the expected value, much better, Mr. Murphy, the expected value of the number of ATMs that are working when the mall opens is 1.73 machines. And again, I do not want to round that. I know that 1.73 machines cannot be working at one time, but that's not what the expected value or mean or average tells us. So I'm going to leave that alone. I am not going to round that at all. And if you did, you would lose some points. We consider that a not fully understanding the concepts. And so please don't round expected values unless specifically told to. What is the probability that all three ATMs are working when the mall opens? So all three are working. Given that, well, boy, that sounds like that conditional probability that we talked about Monday, doesn't it? That's my red flag right there. Given that at least one ATM is working. Well, at least one ATM is working. I sort of just cover up the zero and say, well, at least one, at least one, at least one. And I want to know all three. So the probability that X is equal to 3, i.e. 3 machines are working, given that at least one is working, X greater than or equal to 1. I had my 2.24 was my numerator, that's 3 working. My denominator was adding up those 3 probabilities. I got 0.24 over 0.85, and I just went to my calculator and said, that's equal to 0.282. That's actually lower than what my gut would have said, but it feels like these machines break often. And they said up here that, they sometimes stop working and need to be repaired. So that my gut said it would have been higher, but that's the numbers, that's what it is. And again, I wanted to have our sentence here. The probability that all 3 ATMs are working when the mall opens, given that at least one ATM is working, is 0.282. And in some ways, I'm just repeating the language in the question, but I have my context in here. I've shown the reader some math, et cetera, et cetera. And I think hopefully that's a relatively strong answer that would get a lot of credit, if not full credit. Given that, well, it sort of feels like another conditional probability. Given that at least one ATM is working when the mall opens. Okay, so I guess I have either 1, 2, or 3. Would the expected value of the number of ATMs that are working be less than, equal to, or greater than the expected value from part B? Well, the expected value from part B was 1.73. My gut said it was going to be more. If I say, well, we can't include 0, and these are my only 3 options, it felt like each one of those probabilities might have to proportionally be greater or larger, because those 3 had to add up to 1. So if each one of those numbers gets a little bit bigger proportionally, it feels like when I multiply 1 times a little bit bigger number, plus 2 times that number, which is a little bit bigger, plus 3 times that number, which is a little bit bigger, it feels like my expected value wants to be a little bit greater. So given that at least one ATM is working, again, that means I can cross out that column right there. When the mall opens, the expected value of the number of ATMs that are working would be greater than the expected value from part B, which is 1.73. So I've answered the question, but I think I want to give a little bit more info. By eliminating the probability of 0 ATMs working, the probability for 1, 2, or 3 ATMs working would all increase proportionally, and so therefore I would have a higher expected value. So that was a little different. That wasn't sort of a standard or typical answer. That one I had to think about, and I sort of really like that one. You know, every once in a while, it's really nice to have a challenging problem, even as a stats teacher. So I don't know if I can walk through this one. It's an entirety, but I'll do my best. This is from the 2002 exam. There are 4 runners on the new high school team. The team is planning to participate in a race where each runner runs a mile. So I don't know what you'd call that, the 4x1 mile or something. I guess, you know, runner A runs a mile and then runner B runs a mile. So it's going to take a while. It's going to take a while for all 4 runners to run a mile. The team time is the sum of the individual times for the 4 runners. So I add runner A, runner B, C and D, or 1, 2, 3, 4 to get the team time. That makes sense. And I can add means, right? We talked about that. Assume that the individual times of the 4 runners are independent of each other. Super important. I'm going to underline that. The individual times and minutes of the runners in similar races are approximately normally distributed. That's good. With the following means and standard deviations. So runner A runs a mile in 4.9 minutes. That's actually a pretty good mile. You know, that's really hard to do. These are all under 5-minute miles. These are pretty good runners. And there's their associated standard deviation. So it looks like runner 3 is perhaps the fastest runner. Runner 3 thinks that he can run a mile in less than 4.2 minutes in the next race. A 4-minute mile is 4.2-minute mile is really hard for high school students, really hard for anyone. My gut says it's not likely to happen, but of course I need to do some mathematics, right? Explain. So I said the probability that the time is less than 4.2 minutes is the probability that his z-score is less than, and I just calculated a quick z-score, 4.2 minus 4.5 over a standard deviation of 0.14. What's the probability that the z-score is less than 2.14? Or more than 2.14 standard deviations below the mean. So I just went to my calculator real quick. Normal CDF, -10, -2.14. Now, your teachers may have taught you to type in a different number here. You know, -1,000, minus 2.14. You can see that this number really isn't going to change much, if at all, no matter what my, I guess, lower bound is. And I know sometimes, you know, teachers do 1 times 10 to the -99. I'll leave that up to you and your teachers. What I actually want my kids to think about is, well, why isn't that probability going to change, right? You've changed the lower bound, Mr. Murphy. Well, 10 standard deviations below the mean is pretty much not likely to happen, almost impossible. And so 1,000 standard deviations below the mean is even less likely. There's not much area under the normal curve. How's that? So sometimes I will say to my class, everyone pick a different lower bound, you know, -10, -20, -30, -5,811, really doesn't matter. So I said it is unlikely that runner 3 would run a mile in less than 4.2 minutes. This would only happen about 1.6% of the time, so this is very unlikely. So could it happen? Yes. Is it likely to happen? And the answer is no. So runner number 3 probably is not going to run in the next race, a sub 4.2 minute mile. The distribution of possible team scores is approximately normal. That's good. What are the mean and standard deviation of this distribution? Well, I can add and subtract means, and so I just found the 4 means for the 4 runners, and I added those. And so I felt pretty confident that 18.9 minutes would be the mean or average time. Again, each runner runs a mile, the next one runs a mile, next one runs a mile, next one runs a mile, and I add up those 4 different times. So I can add means. I can't add standard deviations, but I can potentially add up the variances, assuming that my events are independent. Well, their times in this case are independent. So I did underline that, I circled that. So I felt good about that. I felt like, okay, we were told that each one of those runners' times is independent. So I took the first standard deviation and squared it. I took the next standard deviation and squared it. Took the next standard deviation and squared it. So that's a variance, that's a variance, that's a variance, that's a variance. I added up, I guess, my combined variance. I take its square root and I get the standard deviation. So that's part B. What is the mean and standard deviation of this distribution? The mean would be 18.9 minutes. Standard deviation would be 0.3003 or 0.30 or something like that. Let me see if I can finish the last one real quick. Suppose the team's best time to date is 18.4 minutes. So their mean or expected time is 18.9 minutes. Can they run an combined 4 miles, 18.4? My gut says no, but again, I need to do some mathematics. What is the probability the team will beat its own best time in the next race? I said the probability that the team time is less than 18.4 minutes is equal to the probability of your z-score being less than 18.4. That's the time they want to beat. That's their mean or expected value time, 18.9. There's my standard deviation. Probability that z is less than 1.655, so smaller than 1.665 standard deviations below the mean. Again, I went to my calculator and I typed in -10, but you could type in -100, -1,000, whatever your teachers pretty much taught you to do. That's perfectly fine. Your answer is probably not going to vary. And that was 0.04795. And you know, as a stats teacher, we just did inference a couple of weeks ago, and I wanted to compare that to 0.05, but this problem didn't really ask me to do that. So I wanted to, and there was no need to do it here. So the probability that the team will beat its own best time, 18.4 minutes, in the next race is 0.04795. I have context, I have a full sentence, I have some mathematics, and I sort of went down the wrong path here with the 0.05, and I was thinking alpha is 0.05, that's the inference teacher in me. And I don't need to worry about that for this problem. But if it were an inference problem, boy, that's really close to that typical standard alpha of 0.05. And, I'd have to make a decision. And if it was lower than that, I would reject the null hypothesis, but it has nothing to do with this problem. So let's not go there. So anyway, those were, I think, all of the problems that I had for random variables. So let's just check to see if we've done them all. I think we have. So that was good. So real quick, hopefully you're feeling more comfortable with solving different types of random variable questions. I'll just open that up and say probability. Between the probability I did Monday, Luke did binomial and geometric yesterday, and I did some random variables. Hopefully probability you're feeling much more comfortable with. Similar to all problems in AP Stats, you should be able to write down a clear, concise solution in context. It's so important. And every year when we grade problems, we see, unfortunately, students will lose a point, sometimes 2 points, for lack of context. They don't have context. They have some numbers, they have some math, but there's no context, and super, super important. So here's tonight's homework. It's from the 2012 exam, and we're doing some sort of a transformation here, and we want to know what happens to the standard deviation. So Luke will do a great job with that tomorrow. So let's just wind down for today. Hope